Okay, I would like to tell you about the parallel axis theorem. I'm not going to derive this theorem for you. You can get the derivation out of your book. It's pretty straightforward. I am going to show you how to use this parallel axis theorem, how it applies to problems out of your book. Okay, so the parallel axis theorem helps you solve for the rotational inertias about axes that are not through the center of mass. And so it goes like this. First of all, let's agree where the center of mass of this system is. This is a 2 kilograms, 2 kilograms, 2 kilograms, and 2 kilograms. They're connected by very light rods, and I should have told you that on the last one, that these rods that are connecting these things are extremely light compared to the 2 kilograms. That's why we're ignoring them. Okay, well, the center of mass is right at the center. Since they're all 2 kilograms, it would be right at the center. And I'm going to find the I about this axis. Notice how that goes through the center of mass. So this will be my axis. So it's going to rotate. It's going to rotate like this, about that center of mass. All right. Well, then just let's find it. I is equal to 2 kilograms times. Oh, I should tell you that this is 2 meters across. And it's 3 meters down. So that would be 2 kilograms times, it's 1 meter from the edge, squared, plus 2 kilograms times 1 meter from the edge, squared, plus 2 kilograms times 1 meter from the edge, squared, plus, ran out of space here, 2 kilograms times 1 meter from the edge squared, from the axis squared. Okay, so when you add all those up, I think you get 8. I equals 8 kilograms meters squared. Okay, well, here's the thing. The parallel axis theorem says if you want to find the I about an axis that's not through the center of mass but is parallel to that axis, it's got to be parallel to this axis, and you know what I is for this axis, then you just use this equation. I parallel through an axis, I through an axis that's parallel to the center of mass is equal to I through the center of mass plus the total mass of the thing that's going to rotate about that axis times the distance between the two axes squared. Okay, so this is the total mass, and this is the distance between the two axes squared. So let's find the I through this axis. See how they're parallel to each other? Okay, well, if I already know the I through the center of mass, then the I through the other one will equal the I through the center of mass plus an additional term, the total mass of the object, so it'd be 8 kilograms, times how far the two axes are apart squared. So that would be 1 meter. They're 1 meter apart squared. And so that gets me 16 kilograms meters per second. Or excuse me, that gives me 16 kilograms meters squared. So that's the I about this axis. It's a greater I, a greater rotational inertia. Hey, we didn't need the rotational inertia. We didn't need the parallel axis theorem to get this. We could have just used the regular equation. Let's do that just to see that we'll get 16. So if I would have used just the regular equation for this, let me turn off my phone. If I would have used just the regular formula for this, it would be 2 kilograms times 0 meters per second, or 0 meters squared, because isn't that just right on the axis? plus 2 kilograms times 2 meters squared plus 2 kilograms times 2 meters squared plus 2 kilograms times, again, we're back on the axis with this one, so 0 meters squared. So add them up, 0 plus, this is going to give me 8 and 8, so that's 16. Let me just say one other thing that we're assuming. We're not only assuming these rods are light, but we're assuming that these are pretty much point particles. If this were a big giant sphere like I've drawn them, they do have rotational inertia about this axis, but we're assuming that these are little point particles that have a lot of mass. Yeah, that's definitely an assumption we're making. Okay, so you might not be very impressed with this parallel axis theorem because we didn't even need it to do this. In fact, this might be simpler than the actual theorem, doing it this way. So I understand what you mean. So let me show you when this is very handy. Okay, I for a hoop, if this is hollow, this is all air here, and you got this metal band, kind of like my wedding ring, you know, just a metal, just a hollow hoop. Well, the I is going to be just m, the mass of the hoop, times r squared, because all that mass is all at the edge. In fact, you can look in your table, in your book, on page 299, page 299, you can see that there's a bunch of, there's a table of rotational inertias. Let me dim the lights a little bit. See, this is a table of rotational inertias, and it just gives you the equations for these. We're going to actually calculate these, but you need to use calculus to calculate them, so we're going to postpone that for just a little bit more time. Okay, well, if you know the I for that, if you know the I for this is that, what if you wanted to know the I about this axis? So the I about this, if this is the axis rotating here, and we put let's say we hung a hula hoop on a nail in the garage, so it actually went around this axis. It actually went around that axis. What is the rotational inertia about that axis? Well, no problem. I'll use I parallel is equal to I through the center of mass plus md squared. Now, these axes are parallel. They definitely are parallel. See them? Those are parallel. So that's going to be I through the center of mass, which is mr squared. Got that from the table. Plus the total mass, m. And the distance between these two axes is r. And we've got to remember to square it. So that gives me 2mr squared. It's twice as big as when you just go about the one axis. Let's get one more done here. If you look in that table, again, you'll see that for a rod going about its center of mass, if it's a very thin rod, the I is going to be equal to 1/12 ml squared, where m is the mass and L is the total length. Okay, well, what if I wanted to know the I about this axis? See how those are parallel? Well, that I about this far axis would be the I through the center of mass plus md squared. Well, the I through the center of mass is 1/12 ml squared. Oops, I wanted to make that capital. Plus the total mass of the rod, m, times how far these axes are away from each other. So that would be L over 2 squared. So that's going to equal 1/12 ml squared plus, this is going to give me ml squared over 4. If you do that, you'll see that it's 1/3 ml squared.